This is the screencast for section 8.2, example 6, working with indeterminate form infinity times 0. Okay, so this one gets a little bit complicated. The indeterminants infinity times 0 and infinity minus infinity can often be handled by using algebra to get 0 over 0 or infinity over infinity. So our basic L'Hopital's rule gets used at 0 over 0 or infinity over infinity. We're not going to use L'Hopital's rule for multiplication or subtraction, but we need to do some algebra to get to an indeterminate form that uses division. So in part A, find the limit as x approaches infinity of x times the sine of 1 over x. Well, if I plug in or think about conceptually what happens to infinity as I plug in infinity, I get x approaches infinity and the sine of 1 over x approaches 0. 1 over infinity is 0, the sine of 0 is 0. Alright, well, I have that infinity times 0. I'm looking to get a division problem. Well, I only see multiplication, and the sine of 1 over x is a little awkward. So what if I change that? What if I say, let h equal 1 over x? So now I have the limit as h approaches, well, that's going to be 1 over infinity, so 0, but from the right, because we're approaching positive infinity. 1 divided by infinity, getting larger and larger and larger, is going to approach 0 coming in from the right. X is now getting changed to 1 over h, and then I have the sine of now just h, because h was 1 over x. This allows for division. Now I have the limit as h approaches 0 from the right of the sine of h over h. So if I plug in 0, I get 0 over 0, which allows me to use L'Hopital's rule. So now I'll have the limit as h approaches 0 from the right of cosine of h, derivative of the numerator, over 1. Plug in 0, and I get that that's simply 1. Part B, how about the limit as x approaches negative infinity of x sine of 1 over x? Well, same thing. I'm going to say h is 1 over x. So now I have the limit as h approaches still 0, because 1 over infinity is 0. 1 divided by a really, really large number. But now we're approaching negative infinity, so now h is going to approach 0 from the left. And then I still get sine of h over h, which is, in this case, 1. Now, I could have shown my work for L'Hopital's rule, but I've already used L'Hopital's rule to get through that process. Plus, isn't this something we have memorized from chapter 2? Does that sound familiar? Yeah, it should. Now, we left this in h form, but that's okay. Remember, h represents 1 over x. So here's our actual graph, and you can graphically see the limit as x approaches infinity of our x times sine of 1 over x is positive 1, and then like part B, as x approaches negative infinity is also positive 1. So graphically, these represent the same limit because h is the reciprocal of x versus x, and then approaching 0 versus x approaching infinity. Alright, then now try problem number 17. Identify the indeterminate form and evaluate the limit using L'Hopital's rule. So I have the limit as x approaches 0 from the right of x times the natural log of x. Well, if I plug in 0, I get 0 times, now the natural log of x, if we approach 0 from the right, is going to go down to negative infinity. The basic natural log graph curls down that vertical asymptote coming in from the right down to negative infinity. So I don't have a situation where I can use L'Hopital's rule yet, but what I can do is just rewrite x as a denominator of 1 over x. So I'm dividing by x to the negative 1, which is really still x to the positive 1. So natural log stays the same, but now I'm dividing by the reciprocal of x, which is 1 over x. Algebraically, these two phrases mean the same thing, but now I've written it in a division type form. So if I think about what happens as we approach 0 from the right, the natural log of x approaches negative infinity, 1 over x approaches positive infinity. So I have an infinity over infinity indeterminate form now, and I can use L'Hopital's rule. So the derivative of natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. So this is like x to the negative 1. The derivative is going to be negative x to the negative 2. Well, simplify a little bit. I get the limit as x approaches 0 from the right, and then of negative x, that's easy to plug 0 into. I get 0.